Hey, this is Brock LaMeres, and I will be your instructor this summer for EELE 367 Logic Design. The purpose of this video is to give you an overview of the course and give you a little background on myself as the voice in all the videos that you'll be using, and then get you running with Canvas, the new learning management system. Up front, Canvas is new this summer, so it'll be a learning experience for myself, so I ask for a little bit of grace and forgiveness right away as I learn. I think it'll be pretty good from your perspective, as it's just going to look just like Brightspace, where it's just links and folders to upload to. On my side, though, it's taking a little time to figure out where all the buttons are and how to do everything. So if anything goes wrong, don't worry about it. You won't get penalized. And I just ask you, let me know what's wrong and I'll fix it and we'll get through it together. All right, so let's get started. Okay, so the name of this course is Logic Design, and that is what we're going to do. We're going to do a lot of logic design. But to understand what we cover in this course, it really helps to start with the prereq, which is 261, Introduction to Logic Circuits. And this is EELE 261 at Montana State. If you're not from MSU, you should have a course that's similar to this. It's the course that covered things like Carnot maps and number systems and stuff like that. So let's take a review of what we learned in the prereq. So there was a small coverage on what the difference between an analog signal and a digital signal was, just to kind of get us thinking about continuous signaling versus discrete signaling. Then we had a topic or a module on number systems. So this is where logic circuits operate on ones and zeros as their inputs, and they produce ones and zeros as their outputs. But we use those ones and zeros to represent larger numbers, namely in the form of positional number systems. So we need to be able to quickly look at binary numbers and convert them to hex and convert them to decimal. Think about two's complement, encoding and negative numbers and all that sort of stuff. So those things should be familiar to you, all those terms I just mentioned. If they're not, you probably want to review these. Then we moved into digital circuits. So all the logic gates that you use to build logic, so AND gates, NAND gates, OR gates, exclusive OR gates, inverters, those are actually circuits. So those circuits are electronic devices that need power and a ground, and they have voltage inputs and voltage outputs. It just happens that those voltages are mapped into one of two discrete states, which is a 0 or a 1, but they are real circuits. So we had a module where we talked about things like data sheets and current draw and all that sort of stuff. Then we looked at combinational logic design, and this is where we took arbitrary descriptions of a logic circuit's functionality, like a truth table or min-term list, max-term list, and we created or synthesized a gate level schematic. So this is your product of sum products. And we even looked at minimization using K-maps or Carnot maps, but that was a very paper and pencil way to do it. Then we turned our attention to the modern digital design flow, which is using a hardware description language to model the circuit and essentially type out a description of its functionality, kind of like a programming language in that you use a keyboard, but not a programming language because you are actually describing the logic circuit functionality. Then we used a software tool, which was a synthesizer, which could create the gate level schematic for us. And that was a major breakthrough because it allowed us to do bigger and bigger circuits. Then we moved into medium scale integrated circuit logic, which is like multiplexers and decoders and encoders. And the key thing here was to look at a little bit larger combinational logic circuit, but also model it in VHDL, which is the language we use in this class and in the prereq. And then finally, we looked at sequential logic, which was D flip-flops and finite state machines. All right, so now what are we doing here? We're still doing the same thing, but we want to get to larger and larger circuits, and we can only do that using the modern digital design flow. So this class is 100% VHDL. It is 100% using a synthesizer and an implementer tool, namely Quartus, and putting everything on an FPGA or a field programmable gate array. So this is what the course will look like. We are going to design big circuits, things that are bigger than what you could do by hand. So we'll start off, it's a continuation, Module 8. This is all out of the same textbook that I wrote, so we're basically covering the second half. Module 8 goes into VHDL Part 2. This is going to be the more involved constructs of VHDL, such as processes and libraries and variables and things like that, attributes, such that we can model these larger circuits, things that we didn't really have a grasp for in the prerequisite course. Then we do a module on behavioral modeling of common circuits. So this is where we go into things like how do you model a finite state machine using these high level behavioral modeling approaches? How do you build D flip-flops? How do you do all this cool stuff? Then we move into into a new type of system that we haven't modeled in VHDL before, which is memory systems. So we look at how do you build a read-only memory and a read-write memory. Then we step back. Finally, we have everything we need to be able to understand what is underneath the hood of these field programmable gate arrays, these FPGAs that we keep programming. Up until now, we've used them and we haven't really understood what's inside of them. And that's because we didn't have the background for it yet. Now you will, and we can get inside of this thing and look at, oh, what is a LUT? What is a lookup table? What is a configurable logic block? What is a routing network? All that sort of stuff. Then we come back, arithmetic circuits, we look at addition, subtraction, sign numbers, and then we wrap up this whole course with a huge project, and we build a full-blown 8-bit computer in VHDL from scratch. So we learn everything that it takes to build a computer, which just happens to be everything we've covered so far. There's nothing new. It's just we put it together in a form where we can program the computer effectively at a binary level. We'll kind of do it at assembly level, where we insert instructions manually into its read-only memory and we watch this computer run. This module right here is the light bulb moment that will make or break you, because you more than likely, if you're like me, will begin loving logic design and computers even more once you finally realize, holy cow, I know exactly how a computer operates. All right, so let's do this. Let me give you a little background on myself. So I am a professor at Montana State University. I'm in the Department of Electrical and Computer Engineering. I've been here for 20 years. I actually graduated from MSU in 1998 with a BS in electrical engineering. I went to work for Hewlett Packard in Colorado for 8 years, where I designed electronic test equipment for the big computer chip makers. So our customers were Intel and IBM and AMD. And what we built were these test systems that these companies would use to make sure that their integrated circuit would boot up for the first time. So they'd get like first silicon on a chip and it wouldn't work. So they would outfit it with our instruments, and then they would watch the ones and zeros fly around while it tried to boot up, and then they'd figure out what was wrong with it and fix it. Okay. So that experience gave me a lot of background on how the computer industry works and how complicated these integrated circuits are. But it also showed me how to design logic circuits, because that's what I actually did. And so when I came to MSU 20 years ago, I started doing research on how to build computers. And I was particularly excited about this idea of using programmable logic devices, or FPGAs, to implement kind of arbitrarily novel computer systems. So I looked at trying to build like different computer architectures on an FPGA so that it would look like a computer, but it was doing really cool things. And I ended up getting some interest from NASA, and NASA decided to start funding some flight demonstrations of some of our computer prototypes. So we were implementing different techniques to try to overcome errors that were caused by space radiation. And, you know, the space radiation we were concerned about just causes ones and zeros to flip. And so it was kind of an architectural thing. It wasn't like a device physics thing. So it was something I could do, or understand at least. So we started doing all these flight demonstrations, and we were able to go on satellites. We built little satellites pushed out of the International Space Station. We did balloon flights. These are these massive balloons that NASA runs. We did rockets, and I'm trying not to make you sick here, but rockets that just go up and down. And then 5 years ago, we got the big shot, which was we got selected to go to the surface of the moon. And so this year, actually in March of 25, MSU, under my research group's work, actually landed a computer on the moon, and it operated en route to and on the surface of the moon for the entire mission. So this launched in January. We did not build the rocket or anything. It was a SpaceX rocket, and we were bolted to a Firefly Aerospace commercial lunar lander that looks like this. And we were just a little payload on it, but we ran a computer that we called RADPC that actually implemented a lot of the techniques that you're going to learn in this class. So as of March, there's a computer designed by MSU and my research team that is on the surface of the moon. It'll be there forever. It is not going to come back. But what's crazy about this is that all the people that built the computer are students that took this class. This is what the board looks like. This is a little board we did. And this little fella right here that I'm pointing to, the middle guy, that is actually an FPGA. And it has computers on it that are designed in VHDL. So everything you're going to learn is actually something that students before you learned and used to build a computer that ultimately went to the surface of the moon. So this is just awesome. Now, the background of me is number one, it's interesting to know like who's talking in all the videos, but it's really also to show that it's like this isn't just some class that I got assigned that no one else would teach. I mean, this is my passion. This is what I do, right? So I worked in industry. This is the PhD I got was in this area. I teach these classes. I do research in this area. I've written the books of all these classes in embedded systems and computer engineering. So this is really what I get out of bed every morning to do. And so I love this class. I love the content in here, and hopefully you will too. So that's who is screaming into the microphone on some of these videos. All right. So let's now take a look at Canvas. Okay, new this summer is Canvas. Canvas is the learning management system that we will be using, or it's just a website where our course is. This is the first time at MSU that we're going to be using this. We used to use Brightspace, and it's pretty similar to Brightspace from your perspective, just links and folders and stuff like that. But let's walk through how you do it. So number one, you go to ecat.montana.edu. ECAT is like cats for bobcats, and then E must stand for electronic, but ecats.montana.edu. And it takes you to this login page. So you log into Canvas, and what's new this summer is that you have to use your MSU credentials. So you're going to use your net ID, which is this combination of random characters and numbers, and it usually starts with a character, or a number, excuse me, a letter, I'm sorry. And then it says @ and for a professor or an employee, we have msu.montana.edu. As a student, very important, this summer, your call sign is now at student.montana.edu. So you can't log in using this anymore. This is tied to a two-step authentication using Duo. So you're actually going to get this Duo push, and you have to set it up on your phone. Hopefully you've all done it. If you're new to MSU, you just go to the IT page, and it'll walk you through how you install Duo and link it. And I could just email me and I can get you going. So here's Canvas. Right? So when you come into Canvas, what you'll notice is that you always come to this thing called dashboard. Over here on the left is like this toolbar that's always here. So in your account, you can set like a picture in there, which is cool. I encourage you to do it so we can see what you look like. And dashboard is where you come when you log in, and it shows you all the courses that you have. So when you come in, you will at least have 367. If you're taking other courses, they might be in there too. And so you can click on that and you go into it. Okay. So if I click on that, it takes me into the course. And so you can see this landing page right here. If you ever get lost, and you don't know where you're at, you can come back over and click on courses, and it'll give you a list of links to the courses that you're in. So I can get to these other courses I'm enrolled in here, or if you ever want to just get back all the way to the beginning, you can hit dashboard and go back in there. So let's go back into here. And what I want to do is I'm going to switch into student mode so that you see something similar to what you're going to see. Okay, so here we are. You're going to come to this landing page that has a picture of MSU, and it's going to have welcome to 367 Logic Design. So you're always going to come into this page that's called Home. There's 4 tools that I use in my courses. Home is where you land, and you can't get rid of it, so we just got to use it. And then I'm going to have announcements, modules, and grades. So as you go through this course, if you look at this, it's like course description. We already covered that. You're going to learn all this stuff, la, la, la. You will be graded on homework, labs, and a module quizzes and a final project, which is the computer. And this is a 12-week fully online course. In this page, though, what's kind of cool is that you have contact information for myself. Here's my email, phone, website, and a WebEx room. But you also can meet our teaching assistant, which is Aiden. So Aiden is going to be your first point of contact for this course because he will be doing all the grading. He will be available to help pretty much all the time. And so he is who you want to email if you're stuck, if you have questions on grading, anything like that. And then what I do is I back up Aiden as the instructor, but he's the person you want to start contacting first. Prereq for this course is basically 261, right? And so what's important about this though, is as you come down in here, what's going to happen is that you will see the required material that you have, or that's you're needed. And there's a portable lab kit that you need. Okay. So you need to have picked up a lab kit from Deb in the ECE office, or you need to contact me immediately and have it shipped to you. Okay, so you need this portable lab kit. Basically, what's in it is an FPGA board and an analog discovery 2, which is a portable instrument. Okay, all right, then you're going to need a computer, obviously. The problem is that you're going to be doing a lot of VHDL, and if you remember from the prereq, it doesn't run on Mac. So if you got a Mac, you got to get rid of it. You got to figure out a way. It does run on Linux, but you got to get a Windows machine because that's where all the engineering tools are going. So you got to have a computer to do this stuff. You got to have the portable lab kit. You'll get free software that I have videos on how to download and install. And then you need the textbook. Okay. So the textbook is going to be, all the resources, all the examples and stuff. Now, here's how this works. If you want to buy a hard copy of the textbook, go to that link there and buy it at Amazon. It's only $64, $65. It's the cheapest place you'll find it. I don't put the textbook in the bookstore because it's always cheaper through Amazon. If you want an ebook though, we can provide that for you through the library subscription that MSU has, and you can probably think of it as free. You don't have to pay for it. The trick though is you did pay for it because you paid a library fee when you register. So nothing's free. We use that library fee to actually buy subscriptions, and just part of the subscription that we get is to this thing called Springer link. And that gets us access to all of my textbooks. So that's kind of neat. All right. And then you need a camera capable of taking short videos and taking pictures. That's how we're going to demo all the labs. So you're not going to have a TA that you demo to and get checked off. What you're going to do is take a short video of your FPGA board, LEDs blinking, switches going, and that's your deliverable. Academic policies, basically, don't cheat, and cheating means don't turn in other people's work. In engineering, all the problems are solved as groups. So you're going to collaborate, you're going to help people are going to help you, but everybody needs to type in their own VHDL, run their own simulations, do their own quizzes. Cheating is when you just flat out turn in somebody else's work. You just grab their source code or their VHDL code and upload it. That's what cheating is, but you can absolutely work together. You can form groups and help each other because that's how it's done. Okay, so now if I come over to announcements, we'll check that out. Every week, I'm going to put an announcement in here that is going to show you what we're working on for the week. And this is just a reminder. It's redundant to what's in the syllabus. And I want to culminate. I'll end with looking at the syllabus schedule table. If you look at this, we have a set of activities that are due the first week and more activities during week 1 that are due the following week. So the deadlines in this class are all going to be due Wednesday at noon. You have assignments. You have this course logistics quiz that is due the first Wednesday at noon of the class. So you got to get moving right away. Don't wait to log in. I mean, obviously if you got this video, you logged in, but don't wait to do this until the last minute. Then you're going to have activities for the rest of the week that are due the following Wednesday at noon. So that's how the flow is going to work, is you're always going to be working on material and it's due the following week at noon. I will have a reminder for every week, or an announcement for every week that gives you just a reminder. And then I'll also have an automatic announcement that comes up reminding you to turn your stuff in on the Wednesday. Okay, then you come to modules. Modules is where everything is for the course. So every one of these is a page, and you notice here's module 8, 9 through 13. We have a course overview module. If you click on this, this is where you find all the material. So you're going to see always the same flow. You're going to have some learning objectives. That's what you're doing it for. Learning activities. These are what you do to learn the material. So I have these underneath very descriptive call to action words. So watch the overview video, read the syllabus, do the course overview quiz. Want extra credit? Do this. Okay. So every module is going to look like that. And so I'm trying to make it so it's hard not to know what not to do. It's hard to get lost, I guess is what I'd say. Let's look at module 8. Same flow. You're going to have, okay, here's the learning outcomes. Here, this is a 2-week module, and you're going to have, here's assignments, or here's activities: read, watch, do, read, watch, do, read, watch, do, read, watch, do, and then do a lab. Okay. This is the flow. You're going to watch a lot of YouTube videos of me doing VHDL and describing stuff. You're going to do some multiple choice quizzes in Canvas that are automatically graded. And you're also going to do some VHDL design and simulations. So as you look at this, for example, 8.1 has a quiz. You click on that, you do the quiz. 8.2 though is actually a design simulation. So when you click on it, it gives you a description of what you're supposed to do. So in this situation, I want you to design a VHDL system that's called System I that implements this 4-input truth table. And I give you the test bench for it. You simulate it, and then you upload it to an assignment folder. Okay. Sometimes I will have, sometimes I'll give you what the solution should look like. So let me see if I have one in here. I don't know if I do it on this. Okay. Same thing there. I go back. Anyway, I'll show you one in a second. Okay. Important note though, when you look at this, let me go back to modules. Not every module falls within a week. So I also put in here the week and kind of a suggested day to work on this. Course overview, you can do it in one day. Okay. Module 8, spread over 2 weeks. You're going to work on some of it during week 1, some of it during week 2. Module 9, holy boy, holy nugget, 3, 4, 5, and 6. So 3.5 weeks you're going to spend on behavioral modeling. And then 10 is 1.5. Basically, just you got to get used to this idea that modules are, in my courses, are content wrappers. So it's grouped content, but it doesn't necessarily correspond to chronological content. So it's not like every module is a week. The module is content or a type of content, such as behavioral modeling. And then I also try to tell you when to work on that. Okay. So if I come in here, let me show you, if I come in here, let's look at this last module. You look at this, it's like, holy moly, I can't believe how consistent all these pages are. And I know. It's pretty awesome. So I come down here, I'm like, oh, this is so cool. This is so cool. Let's look at this one. Finite state machine design example. I click on that page. This one tells you implement this functionality of a state diagram, use that entity, and I even give you an example waveform. So you get your system looking just like that. Life is good. Okay, so now there's modules. The grading, if you want to see the grades or what your grades are, you come into the grades tool and you get to see every single thing that has a point value associated with it and the date it's due. Okay, Wednesday at noon, as expected, all the way throughout the course. If you want to see that a little bit differently, there's a calendar tool in Canvas that's pretty slick because it actually shows you graphically when the assignments are due. So you'll notice that course starts May 19th. The first 2 deliverables are due on Wednesday at noon. There's a quiz, course overview quiz, and there's also an extra credit opportunity where you send me a professional looking email. Next week, all the rest of the material from week 1 is due Wednesday at noon. Then if I look at the next month, holy moly, everything's due the next Wednesday at noon. It's not a joke. Okay, let me go back and let's end by looking at the syllabus, because the syllabus PDF table is where we want to be. So now I'm sitting here and I'm like, I don't even know where I'm at. I got to get back home. So I can either go to courses, logic design, or I can go to dashboard. So I'm going to go back here and I want to I can get to the syllabus either on my homepage. I have a PDF here, or it's in the course overview. Same document. I build the table in the syllabus first, and then I build Canvas around it. So when I come through all this stuff, your grading is going to look like this. Let me show you the grading first. You have homeworks, you have labs, and you're going to end of module quizzes. End of module quizzes are going to be timed multiple choice quizzes. So they're to emulate like a small exam. So at the end of every module, 8, 9, 10, 11, 12, and not 13, but 12, you're going to have a little timed quiz. Final project is the computer. Work 20% of your grade. This table right here is where you want to really understand the course. This says every week, every module, every assignment, what it's worth in terms of points, whether it's a homework, lab, quiz, or project, and when it's due. So you can see right here, week 1, you have assignments that are due the existing Wednesday at noon. Then you have other things that you're working on that are due the following Wednesday at noon. And then from then on out, week 2, assignments are due the following Wednesday at noon. Week 3, due the following Wednesday at noon. Week 4, following Wednesday at noon. And it goes, and it goes, and it goes. The final 3 weeks of this class are the full-blown computer project worth 200 points. This course, the grading is done with points. So there's 1,000 points possible. You just see these points accumulate. And as you go up, if you get to 900 points, you got an A and you're done. Okay. So remember, this table is the start. Canvas is built around it. So this is the ground truth of the course. Okay. All right. At this moment in time, you are ready to engage in the course. First thing you got to do is get that lab kit. Okay. If you don't have it, go see Deb in the ECE office, 6th floor Cobley Hall. If you're not on campus, contact me immediately and I will get Deb to ship it to you. Then start plunking through the course. Canvas, you come to home, read through the home page. It's your syllabus. Click on this little fella, look through any more details in there. Look at announcements. Why not? It's going to tell you what you're working on that week. Then go to modules and start working through that first set of learning activities. All right, that is it. And good luck this summer. And I look forward to working with you. See ya.